In this section, we'll look at applications of finding absolute minimums and absolute maximums. These are referred to as optimization problems. So each example that we solve will be some type of a word problem. And here in example 1, I'd like to start with something simple, something that will illustrate how the process works and the strategies that we'll use to solve the problems. So example 1 says, find two positive numbers whose product is 100 and whose sum is a minimum. So here, the optimization that's happening is we want to minimize something, and the thing that we want to minimize is a sum. A good general strategy is perhaps draw a picture if that helps with what's happening within the problem, if it's complicated. Then maybe define some variables to create an equation. Once you have an equation, that should be something that you'd like to either minimize or maximize, and you can use derivatives to do that. So let's see, I don't really think drawing a picture will help too much in this problem, but it does say find two positive numbers, and that's making me think, okay, I will define a couple of variables. Maybe I'll call them x and y, and these will be the two positive numbers. Once you have created your variables, you can then go back to the statement and say, well, is there an equation that I can create with them? We are told that the product of these two is 100, so we automatically get this equation. X times y is 100. But there's another equation that we can create as well. Yeah, the product is 100, we have this here, but we're told the sum should be a minimum, so we need to define a sum. Well, I think that's going to be x plus y. This is the thing that we're hoping to minimize, assuming that this is true. We got to call this something. Maybe I'll call it s for sum. So here's my function. It is the sum of the two numbers that I've defined as x and y. The ultimate goal is to minimize this function. Now, the strategies that we have are you take the derivative of your function, you check to see where it's either equal to 0 or where it does not exist, and then they'll give you critical numbers of this function here. Between those critical numbers and possibly a few endpoints, you can find the smallest value that this function has. All right, but there's already a problem. We want to take the derivative of this function, but it contains two variables. It'd be nice if it just contained a single variable, either x or y. That is where this other equation will come into play. We can take this equation and solve it for y. In fact, I'm going to do that next. I'm going to take this equation and say y is equal to 100 divided by x. I can then take this, put it in place of this y, and now I have a function that is completely defined in terms of x, meaning I can take the derivative and find some critical points and go from there. So I'm going to rewrite the function s. It'll be x plus 100 over x. And in fact, s will be a function of just x. So I'll write s of x is x plus 100 over x. And since we want to take the derivative of this thing, I'll write it as x plus 100 times x to the negative 1. Here is the strategy. Take the derivative, find all the places where the derivative is either 0 or undefined, and then we'll check to see if those numbers are mins or maxes, and hopefully we'll come across a minimum. So the derivative of this thing is 1 minus 100x to the negative 2, and we can write this as s prime of x is equal to 1 minus 100 over x squared. Now, x equals 0 is a place where the derivative is undefined, but we're looking for two positive numbers, meaning 0 couldn't be a solution. Even though 0 does make the derivative undefined, that's a place where we have a critical number, we're not going to include it because we could never actually use 0. That means what we have to figure out is, well, where does the derivative equal 0? So I'll solve this equation here. Where is 1 minus 100 over x squared equal to 0? Well, I could add 100 over x squared to the other side of the equation. I'll continue down here. If I cross multiply the x, I get x squared is equal to 100. And if we take the square root of both sides, we get x is equal to plus or minus the square root of 100. which is x is equal to plus or minus 10. So what we did here was we had the derivative. It was this. I set it equal to 0 here, added this to the other side, cross multiplied the x, took the square root, and there were two numbers. There's two critical numbers, 10 and negative 10. Since, again, we're only looking for positive numbers, the only one that makes sense is x is equal to 10. We were looking for a pair of numbers, meaning not just an x, but also a y. What is the y value that corresponds to this? If we go to this equation and put 10 in place of x, 100 over 10 is also 10. This means y is equal to 10 as well. I think that this will probably be the solution. X is 10 and y is 10. The product is 100, and the sum, which is 20, should be a minimum. There is one last thing to check here. We want to make sure that we actually did find a min and hopefully not a max value. To do this, I'm going to draw a number line and figure out values on the derivative of the function s of x. I know that it is equal to 0 at 10. We solve for that. If we're to the left on the derivative, do we get a positive or a negative number? If we're to the right, again, do we get a positive or negative number? That will be enough to determine if there's actually a min at x is equal to 10. Here's the formula for the derivative. If we put a number to the left of 10 that's positive into this, I think x is equal to 1 would be a good choice. 1 minus 100 over 1 is certainly a negative number. So to the left, negative. The derivative hopefully is going to be right on the other side. Let's say you put, I don't know, maybe 20 in place of x. Well, 100 over 20 squared is a number that is less than 1. If you subtract that from 1, you certainly do get a positive number. Why does this mean that there's actually a minimum at this critical number of x is equal to 10? The reason is the first derivative test. This is our derivative. Negative means, okay, the original function is decreasing. Positive means the original function is increasing. That's enough to say, okay, this critical number is definitely a minimum value. So the two numbers are in fact 10 and 10 for both x and y. So to recap, this is the general strategy that we'll take when solving problems like this. Define some variables, perhaps draw a picture if that helps. Create a couple of equations. Eventually, we'll take the derivative of one of those to find critical numbers, and then we'll check to see if we have a min or a max. In example 2, suppose you have 2,400 feet worth of material to build a rectangular fence, and we're going to build this along a straight river. So because we have the river as one of the sides, the fence will only have 3 sides. Can we find the dimensions of the fence in order to maximize the area that's enclosed? So that kind of question makes sense. If you want to build in a fenced-in area, you probably would like to enclose as much area as possible with the amount of material that you have. What I'm going to do is draw a picture for this scenario. So maybe here's the river, I'll keep it simple. And we're drawing a rectangular fence. So maybe we have one side like this, one side like this, and another like this. So we're only building a side here, here, and here. I think some variables that we could define would be x for one side and y for the other. And if we define it this way, that means the other side over here would have to be x as well. The thing we're trying to maximize is the enclosed area with the variables that I have defined. If you want to find the area of this rectangle, that is x times y. So area is x times y. This is the function that I'd like to maximize. Just like in the previous problem, well, you can't just take the derivative of this equation because there's 2 variables in it. There is hopefully some way to reduce this down to a single variable, either x or y. If you go back to the question, it says, suppose you have 2,400 feet worth of material to build this fence. That means the sum of these 3 sides should be 2,400 feet. And that actually gives us a second equation. What is that equation? x plus y plus x equals 2400. I'm going to write that as 2x plus y is 2400. This relationship is always true between x and y. You can solve this for y and put it in place here, and you'll have a function for area completely in terms of just x. Y is equal to 2400 minus 2x. Our area function is now just a function of x. It's x times y, and y is 2400 minus 2x. This is the function that we'd like to maximize. I'm noticing I can distribute the x into the parentheses, so I'm going to write it like this. And written this way, it makes it easier to take the derivative. All right, so if we take the derivative of this function, we get 2400 minus 4x. This always exists, so I'm just going to check to see where it's equal to 0 to find the critical numbers. That's where 2400 is equal to 4x. And if we divide both sides by 4, we get that 600 is equal to x. Okay, great. We also need to know what y is equal to. But here we have an equation that connects x and y, so I'll put 600 here to get the value for y. Y is equal to 2400 minus 2 times 600, which is 1200 minus 2400. Y is equal to 1200. So are these the dimensions that maximize the area that's contained within this fence? That is, x is equal to 600 feet and y is equal to 1200 feet. Notice that this is, if you were thinking it would be a square, this means the object would not be a square. It's only 600 feet on these two sides, and it's 1200 on this side here. And by the way, if you want to know the actual area we get here, that is x times y is the product of these two numbers. That is 720,000 square feet. To determine that it is in fact a maximum, I'll again use the first derivative test. That is, I'll draw a number line and look at the derivative of the area function. I know it is equal to 0 at 600. I'm hoping that it's positive on the left and negative on the right, because the original function will increase, then decrease, creating a largest point. So let's see, I want to choose a number that's less than 600 and put it into the derivative, which is this thing here. You could use 0, for example, and you definitely do get a positive number, which is good. That means the original function is increasing. If you put in a number that's greater than 600, like 1,000, and you put that number here, that's going to be 2400 minus 4,000. That's certainly a negative number. So it's negative on this side. What does this all mean? It means that at x is equal to 600, there is a max on the function a. So this means this number is actually a local max, but because it's always increasing, then always decreasing, it has to be an absolute max as well. So here we go. These are the dimensions for the fence that will maximize the enclosed area. In example 3, we're told a cylindrical can is made to hold 1,000 cubic centimeters, which is 1 liter, of oil. Can we find the dimensions that will minimize the cost of the can? And that's really asking, can we minimize the surface area? Because the smaller the surface area, the less material that you're using to build the can. I'm going to start by drawing a picture. So here we have a cylindrical can, and we're asked about the dimensions that minimize the cost of this can. Well, the dimensions that determine the volume and surface area are this, which is the radius, and then this, which is the height. The volume is given by pi r squared h, and the surface area, which I'll call A, is equal to 2 pi r squared plus 2 pi RH. So here, it helped to know the formulas for volume and area because it told me what the dimensions have to be, R and H. So what we're looking for is a way to minimize the function A, the surface area. Now we are told something about the volume. We're told the volume is 1 liter, or 1,000 cubic centimeters. So from here, we can actually say 1,000 is equal to pi r squared h. This is helpful because, great, now we can take this equation and write it completely in terms of r. The reason we can do this is you can solve for h by dividing r squared and pi to the other side. And I can plug that in place of this h here. So in this equation, h is equal to 1,000 divided by pi r squared. And I'm going to place that right here. Area is now defined as a function of just r. It's 2 pi r squared plus 2 pi r, and h is 1,000 divided by pi r squared. We can simplify this formula a little bit. I can cancel that r with one of the r's in the denominator. I think I'll write this as surface area is 2 pi r squared. Oh, actually, I could also cancel this pi and this pi. I'll get 2 times 1,000, which is 2,000, divided by r to the first. I'm going to bring that r up into the numerator and write that as r to the negative 1 power. If I want to minimize this function, I'll take the derivative of this equation, set it equal to 0, and find critical numbers. So the derivative a prime of r is equal to 4 pi r minus 2,000 r to the negative 2. And I'll write that as the derivative is 4 pi r minus really 2,000 divided by r squared. 0 is a critical number because it makes the derivative undefined. However, r can't be 0. You can't construct a cylindrical can with no radius. So for that reason, we only have to worry about positive values of r. This means I only need to check where the derivative is equal to 0. That is, where does 4 pi r minus 2,000 over r squared equal 0? I'm going to add this to the other side of the equation. I get 4 pi r is equal to 2,000 times r squared. I will multiply r squared to this side and divide 4 pi here. So I'll put that work here. R cubed is equal to 2,000 divided by 4 pi. 4 goes into 2,500 times. So r cubed is equal to 500 over pi. And now we're practically there. If you want to get r by itself, we can take the cube root of both sides of the equation. I'm going to write that answer up here. R is equal to the cube root of 500 over pi. R represents a distance. Since our units were centimeters cubed for the volume, this must be in centimeters. Okay, so the last thing to really check is, if this is r, can we find h? Well, we can put this in place of this r here. But the other thing to worry about is, for this value of r, is it a minimum on this function? We can use the derivative to figure this out. So what I'll do is I'll draw a number line and look at values of the derivative to the left and to the right of this number. So here, I'll check the cube root of 500 over pi, and I know the derivative is equal to 0 here. I want to see if it's positive or negative on the left and positive or negative on the right. For a function like this, it's pretty complicated. I'm going to do this in my calculator. Really, I just care about, okay, do we have a positive or negative number? Just for reference, this number is approximately 5.42. So I think what I'm going to do in my table is I'll check 5 and I'll check 6, and I'm looking to see if I get positive or negative numbers. For 5, I get about negative 17.17. It's a negative number. If I try 6, I get 19.83, which is a positive number. What this tells us is the function, this function, is decreasing and then it is increasing. This is certainly the location of a min, which means we've actually minimized something. This is an absolute min because the function's always decreasing and then it's always increasing. It must be the lowest spot. So great, I can say for sure this is a min on the function a of r. The last thing is, well, what does h equal? To get h, we can take r and put it in place of this r, and what we get is 1,000 divided by pi times this thing squared. Now, a cube root is a 1/3 power, so that means this is 500 over pi to the 2/3. The third because we're cube rooting, and the squared because we are squaring. H is also in centimeters, but these are the dimensions that will minimize the surface area of this can, given that the volume is 1,000 cubic centimeters. In example 4, suppose you have 10,800 square centimeters of material to build a box with a square base and an open top. So there's no top on this box. Can we find the largest possible volume of such a box? Here, I think drawing a picture is helpful. So I'm going to try to draw what's going on here. We have a rectangular box with a square base. So we get something kind of like this. And the top doesn't exist. You can actually look into this box. I drew the height different than the base because we're only saying the base is a square. Perhaps the height could be longer or shorter than the base. Because of this, I think it makes sense to call this side here x. And if this side is x and the base is a square, well, this side is also x. But maybe I'll call the height of this thing y. The way that I've defined these variables, I can now talk about what the volume of this box is. The volume is the area of the base, which is x times x, or just x squared, times the height, which is y. Now, how can I relate the variables to this number, 10,800 square centimeters of material to build the box? This number represents the surface area of this object. So I'll just call that the area. What is the area of this structure? Well, there's one base, and that's x squared. That's the area of the bottom. There's no top, so you actually don't get another x squared. We only get the one on the bottom. But there are 1, 2, 3, 4 sides. The area of each of those is x times y, so that is plus 4x times y. Because there's no top, this is the area of this figure. And we can actually set that equal to 10,800. Now, even though I know that there's 2 sides to each of these, there's a bottom and a top, but you're only going to use enough material to build one figure, so we don't have to account for both sides of it. What we can do with this now is, if I want to maximize the volume, I think we can solve this equation for y pretty easily. It'll be in terms of x, which will go right here. This will be a function that we can take the derivative of and find maxes or mins. If I take this equation and solve for y, I guess I would first subtract x squared. So this will be 4xy is equal to 10,800 minus x squared, and therefore y is equal to 10,800 minus x squared, all divided by 4x. I will take this and plug it in here. We'll have volume just in terms of x's. So the volume, which is now a function of just x, is x squared times 10,800 minus x squared, all divided by 4x. Okay, we can cancel this x with one of those. And I can take this x and multiply it to both of these terms. So volume is 10,800 times x minus x cubed, all divided by 4. And I can also split this up into two fractions. Volume is equal to, I believe 4 goes into 10,800. I think, let's see, 10,800 divided by 4 is 2,700. So we get 2,700x minus 1/4 x cubed. This is the function that we'd like to, in this case, maximize, largest possible volume. I'll take the derivative and find the critical numbers. The derivative of this function is 2,700 minus 3/4 x squared. This always exists, therefore I'm just going to check when it is equal to 0. And I'll put that work over here. I guess what I'll first do is add this to the other side of the equation, which gives 2,700 is equal to 3/4 x squared. Separate this out here. I will multiply both sides by 4 and divide both sides by 3. So if I divide by 3, 3 goes nicely into 2,700. We get 900. So 900 is equal to 1/4 x squared. And if I multiply both sides by 4, I get 3,600. And if I take the square root, I'll get two solutions. I get 60. And even though there are two solutions, x, the way I defined it, is a distance, so a negative number actually doesn't make any sense. It should be that x equals 60 is what we're looking for. We need to know, well, what's the corresponding value of y? I'm going to take 60 and put it in place of these x's, and that will tell me the value of y. I'll put that down here. Again, I'm just going to type this into my calculator. That's 10,800 minus 60 squared, and we're dividing by 4 times 60. And y is actually equal to 30. So my picture is a little deceiving. It should be that y is shorter than x is long here. So I'll just put this is 30. And the units on both of these are going to be centimeters. I'm hoping that these are the dimensions that maximize the volume of this box. How can we make sure that this thing is, in fact, a maximum? I'm going to look at the derivative. So we're running out of space, but I'll put that up here. I'm going to look at the derivative of v. And we defined it in terms of x, which was 60 is the place where it's equal to 0. In this derivative, I'll put a number to the left of 60 and to the right of 60 in my calculator and see if we get a positive or a negative number. And actually, if you put something around like 10 or 0, you get a positive number in the derivative. This means to the left of 60, your volume function is always increasing. If you put, let's say, 100 in place of x, you're definitely going to get a negative number. And that means your function is decreasing thereafter. This means at 60, there is a max. And the reason is the volume function must be increasing always and then decreasing always. There's an absolute maximum at 60, and therefore, these are the dimensions that do, in fact, maximize the volume of this box. In example 5, I'd like to find the point on the graph of y squared is equal to 2x that is closest to the point 1, 4. I think for this one, drawing a picture in the xy plane could be helpful. So here's x and here's y. If you graph this function, it's a parabola because you're squaring one of the variables, but it's not opening in the y direction, it's going to open in the x direction like this. So here is a graph of y squared is equal to 2x. So it's not a function, but it is a parabola that opens up in this direction here. All right, the point 1,4 is actually not on this equation. So 1 comma 4 is up here, let's say. So here's 1 comma 4. What we're looking for is, if you pick a point on this equation and connect it to this point, you can do that for a lot of different points. There's one that should be the closest, which is right about here. So that's what we're looking for. I want to know, what is the xy on this equation that is closest to 1,4? I think what we need to use is the distance formula. And the distance formula says that if you have 2 points, x1, y1, and x2, y2, the distance, which I'll call capital D, between them is, you take the difference of the two x values and square it, and you do the same thing for the y values and square it. If you do that, it'll tell you the distance between these 2 points. And for our problem, we're given the 2 points as 1,4, and the other we can just call xy. Let's put that information into this formula. So here we have D. It's equal to the square root of, if you take the difference of the two x values, I'll say x minus 1 squared plus, and I'll do y minus 4. And I'll square that. Here's my formula. This is the thing I'm hoping to minimize. If we want to minimize the distance, I got to minimize this thing, which means, okay, take the derivative of this, set it equal to 0, find any places it doesn't exist, and then hopefully we'll come across something that is an absolute minimum, because we're talking about closest. Again, we have the same problem. This is a function of 2 variables, x and y. Can we somehow reduce it down to a single variable? Here is something that connects x's and y's together. Well, if y squared is equal to 2x, you can solve this for x by dividing 2 to the other side of the equation. So from this equation, saying y squared over 2 is equal to x is equivalent. I can now replace x with y squared over 2, and we'll have a function now that's in terms of y. So here's my function d. It's the square root of y squared over 2 minus 1 squared plus y minus 4 squared. We're set. This, I can take its derivative, find out where it doesn't exist, figure out where it's equal to 0. Hopefully we come across a minimum. This thing's kind of a pain to take the derivative of because we got this initial square root. So I'd like to point out a fact. If you want to minimize something that is a square root, it's enough just to minimize the thing that is underneath the square root. So I'll say minimize just this part, the stuff that's under the square root. The reason is, if you minimize this thing and then you take the square root of it, it'll still be the minimum. This makes it a little bit easier to work with. So really, the function that we're trying to minimize is y squared over 2 minus 1 squared plus y minus 4 squared. I need to call this something. No, keep it simple. I'll call this f of y. To minimize it, I'm going to take the derivative, and I'm guessing it's going to be defined everywhere, so I'll just figure out where it's equal to 0. To differentiate this, I'll start here. I'll bring down the 2. Copy down the y squared over 2 minus 1. I'll subtract 1 from the exponent. I don't have to write anything here. It's really just a 1. But then I multiply by the derivative of this thing. This means bring down the 2, which will cancel with this 2, of y to the first. And the derivative of minus 1 is 0, which I don't need to write. I now need to differentiate this piece. We get 2 times y minus 4, and the derivative of the inside thing is 1, which we also don't need to write. Let's simplify this thing. I'm going to multiply in the 2 over here, I'm going to multiply in the 2 and the y at the same time. We get this. F prime of y is, if you multiply in the 2, you just get y squared minus 2. If you multiply in the y, you'll get a y cubed minus y. If we do that at the same time, we get y cubed. Again, the 2 here cancels with this 2, and this y brings the exponent up from a 2 to a 3. And then we get minus 2y. Again, if there's a 1 here and you multiply a 2 and a y to it, the minus stays and you'll have now 2y. Here, if you distribute in the 2, we get plus 2y and then minus 8. So f prime of y is actually y cubed minus 8. And this is the thing that we're going to set equal to 0 to solve for the critical numbers. This turns out to be a very easy equation to solve. It's where is y cubed equal to 8? If you take the cube root of both sides, the cube root of 8 is equal to 2. So here, y must be equal to 2. And if y is 2, you can solve for x. 2 squared is 4, and 4 over 2 is actually also 2. I mean, really, that's the point, 2 for x and 2 for y. That's this spot right here. This should be 2, 2. I actually don't think at this point we have to worry about checking that it's a minimum in this function. Just by virtue of our picture, this is the point 2, 2. This was the point 1, 4. Any other point that you draw on this graph is going to be greater than the distance from here to here. So I'm just going to confidently say 2, 2 is the point on y squared is equal to 2x closest to 1, 4. And that's it for this problem. And finally, in example 6, I want to find the area of the largest rectangle that can be inscribed in a semicircle of radius r. All right, so for this one, I think it might be nice to do this in the xy plane. That way, it'll be easy to set up equations that we can work with. To say we have a semicircle of radius r means I could draw a picture like this. So here's my semicircle. The equation of a circle of radius r, centered at the origin 0, 0, is x squared plus y squared is equal to r squared. So we have to know that information. And here, if your radius is just some number r, that means this x value is r, and this x value is negative r. So this is r, this is x is equal to 0, and this is negative r. In fact, any distance from here to here is r. What is the actual equation that I've drawn here? It's the upper half of the circle. You can take this thing and solve for y to figure out what it is. I'll subtract x squared to the other side. So y squared is equal to r squared minus x squared. And if you take the square root of both sides, you get y is equal to plus or minus the square root of r squared minus x squared. Notice you get two solutions. The reason for this is the positive solution is the upper half of the circle, and the negative is the image over the x-axis. So if you actually just want to know what this equation is here, it's the positive solution only to this equation. I'll make note of that up here. This function is y is equal to the positive solution of r squared minus x squared. All right, now we want to inscribe a rectangle inside of this semicircle. And that means something like this. I'll draw in a rectangle here. Here's the rectangle that I will inscribe. How can you figure out the area of this thing? And you have to keep it arbitrary. I think it makes sense to say, well, since I have to figure out the height of this rectangle, I'm going to call this distance x. So here, this is x. And by symmetry, this is negative x. It's just some x value that's smaller than r. Here it's less than negative r. The height of this is determined by this function. If you take this x value and put it in place of this x, it'll give you y. So, is the area equal to x times y? And the answer is actually no. This distance from here to here is x. This distance from here to here is y. So this is xy. It's just this half of the rectangle. Technically, you'd have to multiply it by 2 because it's x plus x. This whole side is 2x. And then this height is y here. Okay, so if we want to write this function as just something in terms of x, I can take this, put it in place of y, and we have the following. A, the area, is now a function of x. It's 2 times x times the square root of r squared minus x squared. And perhaps I'll write it so we have a 1/2 exponent, so r squared minus x squared to the 1/2. In order to maximize this area, I'll take the derivative of this function and find all of the critical values. So the derivative is the derivative of the first times the second plus the first times the derivative of the second, which is 1/2 r squared minus x squared to the negative 1/2 times the derivative of the inside part. R is a number and so is r squared, so its derivative is 0. The derivative of minus x squared is minus 2x. All right, let's simplify this. I don't have to worry about where this thing's not defined. I'm just going to check to see where it's equal to 0. So this thing I'll call 2 the square root of r squared minus x squared. And then this whole entire part here, well, I can see some stuff cancels, like this 2 and this 1/2. Since this is positive and that's negative, I'll put minus. This is minus. Okay, we have a 2x and an x, that's 2x squared. And this negative exponent means it can go into a denominator with a positive 1/2 exponent, which is actually also a square root. So this is divided by the square root of r squared minus x squared. I'm going to set this thing equal to 0. To solve this, I will add this to the other side and go from there. I'm going to place all of that work up here. So to solve this, I'm just going to go up here. I'm going to add this to the other side. So we get 2 root r squared minus x squared is equal to 2x squared over the square root of r squared minus x squared. Notice that you can cancel the 2's from both sides. For this reason, you could have actually just maximized xy, and that would give us the same answer. Anyway, I'm going to take this and multiply it to the left. I'll have this times this, meaning you're squaring the square root. It will leave you with just r squared minus x squared. And that's equal to x squared. I don't really need those parentheses. I'll just erase it, get rid of that and that. I will add x squared to the other side. This gives me r squared is equal to 2x squared. I'll divide both sides by 2. And then I'll take the square root of both sides. Let me just kind of block this off here. We get that the square root of r squared over 2 is equal to x. And there's a plus and a minus, but we're talking about x as a positive number. So therefore, I'm just going to say x is equal to the square root of r squared is just r. So this is r on the top divided by the square root of 2. This is the x value that will maximize the area of this whole thing. How do I know that it's going to be a maximum? Again, I could do that by looking at the derivative. I know this is a critical number. On the left, it's going to be a positive derivative, and on the right, it's going to be negative. It's actually asking for the area itself. This means I have to take this, put it in place of this x to solve for y, and then put it into this equation. I'm running out of space. Let's do that on another slide. So this is what we have. My area function is 2 times x times y. Y was defined as the square root of r squared minus x squared. And we just figured out that x equals r over root 2 is where the maximum must occur. So what I'm going to do is take this and put it in place of this x. We get that y is equal to the square root of r squared minus. If you square this, you get r squared over 2. And that means if you want to combine these into a single fraction, y is equal to the square root of, all right, this is really 2r squared minus r squared all over 2, which is the square root of r squared over 2. So y is equal to r over root 2. So what we have now is our area function is equal to 2 times the x value, which is r over root 2, times y, which is r over root 2 as well. What does this become? Area is equal to root 2 times root 2 is 2. 2 divided into 2 is just 1. And therefore, the area is equal to the radius squared. This is the area of the largest rectangle that can be inscribed in a semicircle of radius r.